So this is chapter 8 about Earth systems and resources. So we're going to talk about plate tectonics, minerals and rocks, soil, and mining. And the two topics that are most heavily questioned on the AP exam are about soils and mining, which we'll do in part 2. So this is going to be more of a review of what you saw in 8th grade. But I do stress that this is still a chapter that you should at the very minimum skim through because you really don't remember as much as you think. The opening chapter, the opening story in chapter 8 is about how although we reduce our use of fossil fuels when we build hybrids or electric vehicles, we of course are going to impact the earth in other ways. So just like we talked about with trash, even if we put them in a landfill or recycle as much as we can, we're still impacting the earth. And with hybrids, it's about using some rare minerals, and they do it similar. They retrieve them similar to the way that we're fracking here in South Texas by shooting super hot water, breaking apart the rock, and getting the minerals that we need, and that is not really environmentally friendly. So make sure you've read the first page on the story. So the beginning, about 12 to 15 billion years ago, the universe was formed, believed in the Big Bang, which is when all the matter and everything that's in the universe was condensed into the size of about a walnut and exploded, sending all that matter outward. Stars were being formed as hydrogen was fusing into helium, helium was fusing into carbon, and all the way up until iron. So all the elements that are on Earth that are naturally made happened in stars. And so we are made of stars. Stardust is what I call it. So our solar system was formed about 4.5 billion years ago, with the sun being at the center. And the heavier elements, which would be iron and nickel, sank towards the center, and the lighter elements like silicon and oxygen floated to the top on Earth. And so the gases that were left became part of the atmosphere. The three main layers of the Earth are the core, mantle, and crust. The core, we believe, is made out of iron and nickel. The inner core, we believe, is a solid ball of iron and nickel, and the outer core is liquid. We believe that the outer core is liquid because S waves, or secondary seismic waves, do not travel through liquids. And seismologists would notice this kind of shadow zone where the S waves would just disappear. We don't know for sure if it's liquid on the outer core. We can just hypothesize. We can't dig that deep. It's also believed that the interaction between the two cores is what gives us our magnetic field, and that protects us from the sun's harmful rays. The mantle is the next level. It is more of a spongy material, as rock is neither solid nor liquid, but just a really soft, soft rock. And it is the convection currents within the mantle that drive plate tectonics, which drives the plates apart or together. The crust is the thinnest layer, and imagine the crust on a piece of bread. It has all the basement rock for our ocean and our continents. Here is the diagram of the layers of the Earth. You do need to know these layers and in order. The asthenosphere is the outer part of the mantle, composed of that flexible rock there. So there's the asthenosphere at the top here. Okay, the upper part of the mantle. And the crust and the solid piece of the upper mantle make up the lithosphere, lithos meaning rock. The continental crust is mostly granitic, which means it's made of mostly silicon and oxygen minerals, or silicates. Since they are lighter and denser, one does not subduct beneath the other. Therefore, when you have two continents coming at each other and they run into each other, they create mountains, which means they just crumble up and move up instead of one subducting beneath the other. Oceanic crust is essentially the opposite. Oceanic crust is basaltic, which is this one right here, which is mostly made of iron and magnesium. Most ferromagnesian minerals are going to be dark natured, which makes them mafic, whereas on the other hand, continental crust or granitic is lighter, and that's called felsic. Oceanic crust or basalt, when since it's more dense, it will subduct. So if you have two oceans coming at each other, whichever has more iron and magnesium to make it more dense will subduct beneath the other. And when an ocean is colliding with a continent, it will also subduct beneath that. We think that what's going on to generate the heat in the center of the Earth is radioactive decay of potassium, uranium, and thorium. And when you have radioactive decay and you have these radioactive elements which are unstable and they decay to become more stable, it releases energy. And so energy in this case is in the form of heat. And so they believe that that's the heat that drives the convection currents. Continental drift. Alfred Wegener was a German meteorologist, and in the early 1900s was checking out a map of the world and noticed that South America and Africa seemed to go together really well if you were to cut them out and put them together like a puzzle piece. And so he did that with many of the continents and noticed, wow, they could really fit together to form one giant landmass, which he named Pangaea. The one large ocean was called Panthalassa. And he also noticed several pieces of evidence. And if you notice here on the bottom, these two graphics are not in your book, but here the Mesosaurus was a swimming reptile and the Glossopteris was an ancient fern. And these are organisms where the seeds of the Glossopteris could not have swam across oceans. It's a seed. The morphology of the Mesosaurus suggested it could not have been able to swim across the Atlantic, where's my mouse, to make it from South America, South America, to southern Africa. Therefore, it seemed logical that at one time those continents were together so that the Mesosaurus could roam freely between them. The Glossopteris is a little bit more convincing because if you notice, it covers so many continents. It covers all of them, although North America is not on here. And so it didn't really make sense that one species of fern fossils was discovered on all the continents if they had never been connected. Glacier evidence was also found where glaciers, as they retreat and move across continents, scratch it up, leaving footprints essentially, and they were able to match up very similar footprints across the continents that could not have happened if they weren't joined. The last one here is about mountain ranges. What geologists noticed with these mountain ranges in brown here were almost identical in terms of their strata or the layers of rock, and frankly, geologists can't come up with another reason for that, because if they're identical beds or strata, you can't have that unless it was one continuous mountain range. So his evidence was pretty convincing back in the early 1900s, but the problem was that he did not have a mechanism. He could not explain how the plates actually moved. He suggested that the plates actually scratched along the ocean floor, but when you looked at the ocean floor, there were no scratches. There was no evidence to support that. In 1960, Harry Hess came along with the idea of seafloor spreading. He said that as the crust would separate, new ocean floor would be created, and then at other places where it was subducting, it would basically eat away, well, swallow, I guess, the other ocean or ocean crust. So kind of conserving overall the amount of crust. Because he was able to connect seafloor spreading to continental drift, they came up with the theory of plate tectonics. And what's interesting about plate tectonics is that it's a fairly new theory. It did not come about until at least the 1960s. And plate tectonics says that the Earth's lithosphere, or the rocky crust, is divided into plates. And like a hard-boiled egg that's been dropped, and the shell would represent those plates. And those are in constant motion. They kind of float on the mantle, and that convection current going on in the mantle is what's driving those plates apart or together. This picture here is showing you the glacier evidence. So here's a map of all the different tectonic plates on Earth. The Pacific plate here is called the Ring of Fire because of all the earthquakes and volcanoes that go around the plate boundary. The triangles here represent subduction zones, so that means that as this Nazca plate is running into the South American plate, since this is oceanic crust and this is continental crust, the oceanic crust will subduct beneath the continent, and that piece of crust will start to melt, and then it'll start to rise, and it forms mountains. So in the case of South America, that was the Andes Mountains. Over here in North America, the same thing was happening at one time with the Cascade Mountains. Here, where the Juan de Fuca plate is running into the Antarctic plate, you have island arcs. So when you have two oceans colliding with another, you get island arcs, and that's what the Aleutian Islands are in Alaska. Spreading zones, the most famous spreading zone is right here. This is the Mid-Atlantic Ridge. So where you have the red, you have spreading zones, so it's splitting apart. Here you have that also going on in land. This is a triple junction in Africa. So right here where the Red Sea is, it's actually opening and getting bigger. You also have transform faults along these spreading centers. I keep losing my mouse. Here it is. And so you have tons of earthquakes that also occur along spreading centers. So there are three types of plate boundaries. There's divergent, convergent, and transform. In divergent, they're simply moving apart, which makes sense because that means to diverge. So when plates are moving apart, new crust is being generated. In convergent, you have three types. You have ocean-ocean, ocean-continent, and continent-continent. Whenever ocean is colliding with another ocean or continent, it will subduct because it's more dense, and that will create mountains generally on the edge of a continent. If ocean is colliding with another ocean, you get island arcs. And if continents are colliding, since they are very similar in density, one does not subduct beneath the other, they just kind of crumble up and rise, creating mountains. Transform fault boundaries are those where you have two plates that are sliding past each other sideways. One is not moving up or down. That's what's going on at the San Andreas Fault in California and why they're so prone to earthquakes. Here you have the illustration. In letter B, it's not really indicating whether or not that's ocean versus continent or ocean versus ocean, but one of this one here on the left is definitely a piece of ocean since it's subducting. But just realize that if it were two continents, one would not be subducting. Here is a hot spot, and the Hawaiian Islands are the most classic example of a hot spot. There is a weakness in the crust, in this Pacific crust, and over time the magma will rise and come through the weakness in that crust and create a volcano. It moves off of the hot spot, and we can tell that it's moving to the northwest just because of the layout of the islands. So as it moves off, then another volcano will form, and then it moves off and another volcano will form. So over time, you know, in 500,000 to 1,000,000 years, the main island of Hawaii will move off the hot spot and another volcano will replace it. If you look at this Earth right down here, you can see that this hotspot has been active for millions and millions of years. And this is showing you that at one time, this Emperor Seamount chain was indicating that the plate was moving north. Now we can see that it's moving northwest. We just don't see those volcanoes anymore because they are underwater. They've been eroded away. Earthquakes are when you have two pieces of rock that are sliding past one another, or one will rise up and the other side will rise down. Transform means they're just sliding past one another. So the fault is basically the crack or the fracture in the rock. And when the tension builds up between these two rocks and it releases that energy, like you were going to release a rubber band, that's when you have an earthquake. There are thousands of earthquakes every year that are basically a 2 on the Richter scale. You don't get very many that are 8 and above. But when you do have an earthquake of 8 and above, that's pretty drastic and devastating to the area around you. The fault zone is where movement has occurred. We live right next to a fault zone, the Balcones fault zone, and it's because of this fault zone that we have the hill country, where, because you can see it right when you're on 10 and you're going up towards Bernie, you see all of a sudden the hill country, where you are on I-10 is flat. That fault zone has since become inactive, so we don't expect any earthquakes to happen. The epicenter, well, let me back up. The focus is the actual spot where the rock erupts and causes the earthquake. The epicenter is the spot on the surface directly above the focus. And when you have seismologists around the world trying to figure out where that earthquake occurred, they're looking at the data from at least 3 different locations so they can triangulate the location of the epicenter. The Richter scale is how we measure earthquakes, and that's in terms of intensity. So, and it's a logarithmic scale. So here you see if it was a 7, that's 10 times greater than the 6. A 7 is 100 times greater than a 5, is 1,000 times greater than a 4. So you can see that as you move up in numbers, they're pretty powerful. But we have earthquakes all the time all over the earth that we never really feel because they're so minor relatively. The rock cycle is made up of 3 different types of rocks. You have igneous, metamorphic, and sedimentary. And the oldest rocks on Earth are about 3.7 billion years old, and they've been located in Australia. And the reason why it's hard to find really ancient rocks is because of the rock cycle. They're constantly being recycled. So with igneous rocks, those mean born of fire, and so those come from magma. And when the magma cools and hardens, it forms rock. And so if it has really large crystals, that's called intrusive, because the magma cooled very slowly as it was still within the earth. When you have extrusive, that means the grains or the crystals are so small, or they don't exist at all, because they cooled very quickly once they got above the earth. So when you have pumice or scoria, those are called lava rocks. Those show up because they shot out of a volcano. So because they shot out of a volcano, they cooled so quickly that no crystals had time to form. So in terms of granite and basalt, the 2 most common igneous rocks, those are what make up the crust. Granite, the continental crust, is intrusive igneous, and basalt, the ocean crust, is extrusive igneous. Sedimentary rock comes when you have sediments that are formed from all different kinds of rocks being basically glued together. It's compacted, which means it's squeezed together, all these different sediments, and then cemented through natural minerals that were dissolved in water. You can also have organic sedimentary rocks. That would be coal. That would be coquina, which is a rock made entirely of ocean organisms' shells. And you can also have chemical sedimentary rocks, which just means that ocean water evaporated and left behind the rock, which could be gypsum or salt, rock salt. Metamorphic rocks come when you have basically any other type of rock that is subjected to high temperature and pressure. And what happens is the minerals get realigned and you create a new rock. So heat and pressure are the two keywords for metamorphic. Weathering and erosion. Some people think that weathering and erosion means the same thing, and they don't. Weathering is basically the breakdown of the rock into smaller pieces. And you can do that physically / mechanically or chemically. So you can see here in this example that here water has entered cracks and the water freezes. When the water freezes, it expands. So over time, it'll break the rock. That's weathering. Here you have a biological agent, which is this root, that as it grows into the rock, it will break it apart. Chemical weathering is when you have rock that is broken down by chemical reactions. So in here, in this case, which looks like it looks like natural bridge caverns. I'm not sure which one that is. You have water that has carbonic acid in it, and it has carbonic acid because the carbon dioxide in the atmosphere mixes with the water. As it drips down into a rock like this, which is limestone, it's changing the rock and making it weather. So you have all these really cool formations. Erosion, on the other hand, is taking that rock and moving it somewhere else. So weathering is the breakdown of the rock and erosion is the carrying away. And erosion can happen by wind, water, or ice. Or even living organisms, they can carry it other places. And then once that rock has eroded, it's got to go somewhere, and so it will deposit somewhere. And so a deposition is just simply that accumulation of the eroded material, and it'll be deposited into beds or strata, as you see here. All right, so that is the end of part 1.